Okay, so today we have two sections to talk about. We have the comparison test stuff, which is from 10.5, and then we have ratio and root tests from 10.7. So where would we like to begin? Yes, sir.
We do 19 and 5.
Yes, 19. So they're saying use a comparison test or a limit comparison test to determine the following. And you said 19?
Yes.
Okay. So, and this is from 10.5. It says sum k going from 4 to infinity of 1 plus cosine squared of k divided by k minus 3. Okay. So they say to use a comparison test or a limit comparison test. Okay, there's a couple different ways to go here. One of them I like the most, and that is notice that the top here is 1 plus something that ranges between 0 and 1. Like cosine squared of k, the smallest that could ever be is 0, because it can't be negative. And the biggest it could ever be is 1. So would you agree with me if I said the following, that this is strictly less than the sum k going from 4 to infinity of 2 over k minus 3? Okay. Let's see. Do I like this? Just a second. This is true, but it is not helpful. Okay, and why do I say that? Well, let's look at this for a second. What is this sort of kind of like? Sort of like 1 over k, right? The 2 could come out, then I have 1 over k minus 3, but it starts at 4, so this is kind of like a 1 over k situation. And does that converge or diverge? It diverges. So what I know is the thing that I want to know something about is smaller than something that diverges. That's unhelpful. Does everybody agree? If something is smaller than something that diverges, it still could diverge or it could converge. So that's not so helpful, so this wasn't such a good comparison. Is there something I could do that's better? Well, this thing is also bigger than or equal to 0. So that means that this thing is greater than, or potentially, well, it's greater than, sum k going from 4 to infinity of 1 over k minus 3. Does everybody agree with this? This one's bigger than this one. Well, I can definitely put equal to, and it's not false, but it's also strictly greater than, because because this thing is added in as a positive number in some of the terms. So this one is definitely bigger than this one, considering all the terms.
Okay.
Agreed?
Yeah.
Okay. And what did we just say about this kind of 1 over k type thing? This thing diverges. Does everybody agree? Mm-hmm. So this one's bigger than something that diverges. So what happens to this one? It must also diverge. So it's kind of like this one adds up to infinity, and this one's even bigger. Okay, so since sum k going from 4 to infinity of 1 over k minus 3 diverges, we know that the sum k going from 4 to infinity of 1 plus cosine squared of k over k minus 3 also diverges by the comparison test. And this is one of the very, very few places that I would ever really want to use a comparison test. Typically, I like the limit comparison test much, much better, but comparison tests work really well when you're bounding things. And so like here, I can bound 1 plus cosine squared of k by 1 below, or by 2 above. So comparison tests are really good when you're like, well, I know that this thing is bigger than 1, or it's smaller than 3. They're not so great if you're just trying to do, like I wouldn't use a comparison test if I were trying to prove that this is sort of like 1 over k. I would just do a limit comparison test. Did you have a question?
Not for this one.
Okay. Yeah, which one?
15 for
15. In which section?
10.5.
Okay. 10.5.
No, 15.
15. Okay, number 15, we have sum k going from 1 to infinity of 4. Sum k going from 1 to infinity of 4 to the k over 5 to the k minus 3. And it says to use a comparison test. Okay, so something that I noticed right off the bat is if this minus 3 weren't there, then what would this be like? What's that? Yeah, it would be geometric, and it would converge because the ratio is 4/5. Correct? So this is sort of kind of like a geometric, but it's not geometric. But maybe we could compare it with a geometric and see what we get, okay? So let's see. So let's do a limit comparison test this time. And limit comparison test, we're going to take the limit as k goes to infinity. And I just want to be sure that I'm putting the correct sequence on the top. Yes. Yeah. Okay, so we put the one we don't know about on top. We put the one that we do know about on the bottom. Okay, so we know that the sum of these guys converges because it's a geometric with r less than 1. This one we don't know, but it seems that they might be similar. So what do we get? We get limit k goes to infinity of 4 to the k over 5 to the k minus 3 times 5 to the k over 4 to the k. All right, so the 4 to the k's cancel, and we get limit k goes to infinity of, we have 5 to the k on top over 5 to the k, oops, 5 to the k minus 3. And now we can divide, if we wanted to, we could divide top and bottom by 5 to the k. Okay, if we divide top and bottom by 5 to the k, I get limit as k goes to infinity. 5 to the k divided by 5 to the k is 1 on top. 5 to the k divided by 5 to the k is 1 on the bottom. And minus 3 divided by 5 to the k is minus 3 over 5 to the k. And of course, as k goes to infinity, 5 to the k goes to infinity, and 3 over infinity is like 0, and I end up with 1. Now, what does that mean in terms of the limit comparison test? That I got a 1. Yeah.
It either means converges or do it the same or
Yeah, what it means is whatever this one does when you take the sum, this one does when you take the sum. Okay, and that's true when? What's the rule for the limit comparison test?
Greater than 0.
Yeah, if it's greater than 0, and then there are rules for if it is 0, and there's a rule for if it is infinity. But if it's not 0 and it's not infinity, it's somewhere in between, then whatever the bottom one does, the top one does. Yeah.
why is it 1 or greater than 0?
Why does being greater than 0 mean they do the same thing?
Yeah.
Yeah, because basically it's saying that they have a similar rate of growth. So a way of thinking about it is this thing is growing as k gets big, this is going somewhere. As k gets big, this is going somewhere. But are they going kind of the same place? Because if they were going to basically the exact same place, then what would you expect the ratio to be?
1 to 1.
1,
Okay.
right? So if they were going to the exact same place, which these pretty much are, because when this gets huge, like this is 10 million, -3 doesn't really do much for it, right? So the -3 really almost, as k gets big, it's almost not even there. So what it's saying is these two things do the same thing, and you get a 1. But the thing is, what if there was like, I multiplied the top by 2? Then I would get a 2. And then it's kind of like, so are they doing the same thing or not? It's like, well, yes, they are. It's just that the top is multiplied by 2. Does that make sense?
Yeah.
So it's kind of like no matter what you get, if it's in between 0 and infinity, it's just 1 times something.
Okay.
But if it is 0, that's kind of different. And if it is infinity, that's kind of different. And you can think of it, if it's infinity, that means this thing is getting big a lot faster than this thing. Correct? So the top is getting really big. This guy can't keep up. So that means this is a lot bigger. So if you know that the thing on the bottom, the little guy, is going to infinity, what can you tell me about the thing that's growing a lot faster? It's going to infinity. So that's the rule, is that if you get infinity and this one diverges, this one diverges. Other way around, if this goes to 0, that means this is getting much smaller than this one is, right? This is much smaller than this. And then if you say this one converges, the big one converges, and then this thing that's a much smaller also must converge. So it actually does make sense, the rules. It's like either they're sort of kind of doing the same thing, that's between 0 and infinity. Even though it seems like, well, that's not really the same thing. But even if I multiply this by 1,000,000, they're really doing the same thing. Or it's 0, which means that if this one is small, this one is small. Or it's infinity, which means if this one is big, then this one is big. And that's it. Yeah, no problem. Another question. Yeah.
Number 11 on 10.7.
Sure. Number 11 on 10.7. Oh, yeah. Okay, so 11 says the sum, k going from 1 to infinity of -1 raised to the k plus 1 times 10k cubed plus k divided by 9k cubed plus k plus 1 all to the k. All right. Okay, and they say, see if it converges absolutely or it diverges. Now, what do they mean by converge absolutely? That means, does it converge if you take the negatives away? In other words, if you took the absolute value of all of these guys, would it converge? Does that make sense? So what I'm doing is basically there's this minus that's going, making one minus plus, minus plus, minus plus. I'm saying turn it all to pluses. I like to think of like series as there's a bunch of light switches, and each term has a light switch that either makes it positive or negative. Right now, it's every other, right? It's on, off, on, off, on, off. And I'm saying turn them all on. Does it converge when they're all on? Now, you answer this question for me because this is interesting. If I tell you, if I turn all the switches on so that they're all positive and it converges, what do you think if I turn them all negative? Why?
If it converges, it's all positive. That means you're adding fractions, which means and then if you turn them all negative, it should probably converge to. So all you're doing is adding a negative sign to whatever it converges to.
That's right. All you're doing is changing it all to negative, right? So if they're all positive and it converges to, let's say, 2, then if you turn them all negative, what would it converge to? Negative 2. Does everybody buy that story? Okay. So if everything's positive and it converges, then when everything's negative, it also converges. So what could you tell me is if I just went through helter-skelter and said, okay, this one's positive, this one's negative, not even every other, I'm just like hitting random guys and saying, this one's positive and this one's negative, positive, positive, negative, negative. And then I get all the way through, but I tell you, if they're all positive, it converges. And if it's all negative, it diverges. Where will, if I just hit some positives and some negatives, where will it live? The answer.
The negative diverges.
So yeah, if I make all of them positive, let's say here's a number line. And if I make all of these guys positive, it converges up here to, let's say, capital M. And if I make them all negative, it converges down here to negative M. Then if I change some of them to positive and some of them to negative, where will the answer be? It has to be, well, I don't know if it's close to 0 or not, but it's certainly in between negative M and M. You're not going to get like 3M, because you would have to be bigger than everybody being positive. So it can't be bigger than M, and it can't be smaller than negative M. So guess what? It converges. It can't be infinity because it's between negative M and M. So this is what we talk about when we say something converges absolutely. It's turn them all to positives and see if it converges. If it does, then with the negatives in, it certainly converges as well. Is everybody with me? Okay, let's do this problem then. So the first thing that I'm going to check for is, does it converge absolutely? So I'm going to take out the negatives and I'm going to do a root test. The reason that I want to do a root test right here is because I have something raised to the k power. That's like the ideal situation for a root test. Because in a root test, you take the kth root of the sequence. And so what I'm going to do is I'm going to say, let's take the kth root of 10k cubed plus k divided by 9k cubed plus k plus 1 raised to the k. When we take the kth root of something raised to the k power, we just get out the limit, as k goes to infinity, of 10k cubed plus k divided by 9k cubed plus k plus 1. Now, can anybody tell me what is that limit? 10 ninths, right? Just by, we know we have this highest power of k on top and bottom is cubed. And so we just take the coefficients out in front and we get 10 over 9. 10 over 9 is significantly, for the root test, a bigger number than what? 1. And if it's bigger than 1, what happens to the original series? Now remember, the original series in this case doesn't have negatives. So what happens? It diverges. It needs to be less than 1 to converge. Bigger than 1 diverges. Equal to 1, we don't know. We have to do something else. Okay, so what I've got so far is therefore the sum k going from 1 to infinity of 10k cubed plus k divided by 9k cubed plus k plus 1 to the k diverges by the root test. But I am not done. Because I haven't figured out, it could be that this thing still converges. Okay? It just doesn't converge absolutely. So first I was testing to see, does this thing converge absolutely? In other words, if I take away the negatives, does it converge? And I said, if I take away the negatives, it diverges. So it doesn't converge absolutely, but it still could converge, we call it conditionally. Like it needs its negatives to converge. So now we need to do some other test. And the other test that you typically do at this point is you do what's called a test for absolute convergence. Yeah, I'm not loving this. Just one second. I'm fine with the problem, but just a second.
Do you want to do like the alternating series test?
You do.
Yeah,
You want to do an all.
Because that one is 10.6.
And that's the next thing. Yeah, that's not good.
Because this is 10.7.
Yeah. Okay. So here's the thing. That's really bad. So I don't know how this got messed up like this, but what I'm going to do is, since there are problems in 10.7 that you need to use 10.6, I'm going to push that homework. So I'm going to push it up to the day that we do 10.6. Okay. So I can finish this problem because it's interesting, but technically you need to see some stuff in 10.6 to better understand this problem, because some of the stuff I'm saying right now, you might be like, I don't remember doing that. And that's because you haven't. Okay. So don't feel bad, but do watch the 10.6 lecture. And so I'll change that as soon as I get back to my office today. So 10.7 stuff will be due with the 10.6 stuff, not with the 10.5 stuff. I think that when I taught this before in maybe a different edition of the book, it went like section 10.5 and then 10.7 was the next section. And then alternating series came next. And they switched them, but then they put problems in where you need this stuff. So that's not the best. Anyway, I'll fix it. Sorry about that. Anyway, let's finish the problem though. I'll just kind of give you a little bit of learning. What we would do is we would do what's called the alternating series test. And basically all that you do with an alternating series test is you take the limit as k goes to infinity of the sequence itself. Which is 10 k cubed plus k over 9k cubed plus k plus 1 raised to the k. Now this is the same as the divergence test, but in the case of an alternating series where it flips back and forth, every other is plus, minus, plus, minus. That's what we mean by an alternating series, is minus, plus, minus, plus, minus, plus. Then if we do this test where we just test the limit of the sequence itself, if we get 0, it does converge. The original series converges with the minuses in. So how do we do this? How do we take this limit? Any ideas? Because it's kind of like it's infinity over infinity to the infinity.
Could you try to do ln first and say it equals L and then do the ln of this stuff?
Yeah, that's good. So whenever you have something raised to a power and you're taking the limit as k goes to infinity, a good idea would be, say, let's call that L, and then take the natural log of both sides. So we could say that ln of the limit as k goes to infinity of all this stuff is ln of L. Now I could flip the limit and the ln, and I get this is equal to limit as k goes to infinity of ln of all this stuff to the k, which is equal to, now since it's ln of something to a power, I could pull the power out in front if I wanted to. And I could write this as limit as k goes to infinity of k times ln of 10k cubed plus k over 9k cubed plus k plus 1. Okay, is this any better? Well, what's the form that I have right now? If I plug in infinity, I get infinity here. What if I plug in infinity over here? So I kind of get what? Yeah, I get infinity over infinity, but actually I do know the limit as k goes to infinity of what's inside.
Right.
What is it? 10 ninths, and ln of 10 ninths is not 0. Right, so I'm getting like infinity times something that's non-zero. That's infinity. Correct? So this thing is infinity, which is definitely not 0. And so what this tells me is that this thing still diverges. Maybe this shouldn't be shocking to us, because this is something that if you look at what's inside here, this is basically something a little bit bigger than 1. Agreed? So you can kind of think of this as like when k gets big, this thing inside is kind of like 10 ninths.
Right.
Then you're taking 10 ninths and raising it to the infinite power over time. So you're adding bigger and bigger things, but they're minus and then plus and then minus and then plus. So it's kind of like you're starting at 0 and you're adding like 10 ninths, and then you're subtracting something even bigger. Then you're adding something even bigger, and it's going out, it's just going crazy. It's oscillating all over the place. It's a mess. So this shouldn't be surprising that this thing adds up to basically nothing. So our conclusion would be this thing adds up to infinity. So we can say, therefore, the sum k going from 1 to infinity of -1 raised to the k plus 1 times 10k cubed plus k divided by 9k cubed plus k plus 1 to the k diverges technically by the divergence test. We were doing sort of an alternating series test, but if we don't get 0, then technically we just did the divergence test and didn't get 0, so it must diverge. So an alternating series test is kind of like if it is 0, then it converges, and if it's not 0, it diverges. But that only works if it's an alternating series. And you'll learn more about that when you listen to the lecture on 10.6. So I'm gonna, like I said, I'm modifying things. 10.5 is due today. 10.6 and 10.7 will be due on Monday. Okay. Other questions? Yes, sir.
Could you do 27 and 5?
Yeah. 27 on 10.5. Okay, 27 on 10.5 says the sum k going from 1 to infinity of 2 plus -1 to the k divided by k squared. All right, and then they ask to use a comparison test, is that right? Yes, or a limit comparison test. So what I would like to do is I'd say, okay, first of all, this thing is either -1 or it's +1. If it's +1, then I get 3 on top, right? If it's -1, I get 1 on top. So what I could say is that this thing is always, this is a bigger series than the sum k going from 1 to infinity of 1 over k squared. Does everybody buy this? If all of these were -1s, that's what I would get. But some of them are +1s, so I get 3s on top. So this series is strictly bigger than this series. All right, does this series converge or diverge? Why? Yeah, does anybody know the official reason why this thing converges?
It's a P series.
It's a P series with P equal to 2, but technically what do you have to do? What has to be true about that number in order to get convergence? Bigger than 1. That's exactly right. So if you have 1 over k to the p, and p is bigger than 1, then we get convergence. If it's less than or equal to 1, it diverges. Okay, but this one converges. So I'll say which converges. Because it is a, let's see, is that helpful? That's not even helpful. So I probably needed to do the other way. Okay, but it's still good to think about. So if you say that something's bigger than a convergent series, that's not helpful, right? Because it could diverge. But what I could do is I could say, okay, then this is certainly smaller than sum k going from 1 to infinity of 3 over k squared. Correct? And if you wanted to, you could factor out that constant, which is equal to 3 times the sum k going from 1 to infinity of 1 over k squared, if you don't like to have the 3 up there. And then this is a p-series. That, what? We just said that converges. So 3 times it also converges. And so now this thing's smaller than something that converges. So it converges by a comparison test. So what I would say is, since sum k going from 1 to infinity of 3 over k squared converges, because it's a p-series, we know that the sum k going from 1 to infinity of 2 plus negative 1 to the k over k squared converges by comparison test. And we're done. Sound good? Other questions? I think somebody asked a question on here. Let me look. Oh, okay. They took it back. Anything else that anybody wants to look at or someone online wants to look at? Yes.
Number 18.
18? Okay, let's look at number 18. So we've got sum k going from 1 to infinity of 1 over k times 10 to the k. We have sum k going from 1 to infinity of 1 over k times 10 to the k. All right, and one of the greatest things that you can get a feel for when you're doing these things is what exactly is kind of the tipping point where things start to converge. And we know that what happens to 1 over k? It diverges. But what happens to 1 over k squared? It converges because it's a p-series. So in fact, if it's anywhere over 1 over k to, let's say, the 1.1, that converges, correct? Anything over 1. So it's kind of like, this is so close to converging, but it diverges. So what if I multiply it by a little bit more? In fact, this is not a little bit more. 10 to the k is going to get huge. So what would be our guess here? Is the bottom getting big fast enough for this thing to converge? Just a guess. Yes, I would agree as well. Like 10 to the k seems like a bigger number than k. And k, 1 over k times k converges. So just intuitively, I'm like, well, this certainly converges, but how do I show it? Is everybody with me? So if I'm just trying to figure it out in my head, like, what do I even think this thing does? I would say, oh, if this was k times k, it's 1 over k squared, which converges. And this is even bigger than k. So certainly this converges. So what I might do is I might say, okay, then let's do a limit comparison test maybe with something close. What's something that I know would converge? I would say 1 over k, but 1 over k doesn't converge. It diverges. So comparing it with 1 over k seems like a pretty bad idea. Yeah.
Maybe try comparing it to 1 to the k over 10 to the k.
1 to the k, or just 1. right?
Right.
Yeah, I agree. How about if we compared it to 1 over 10 to the k? What kind of a series is this if the k isn't there? Yeah, this is geometric and R is what? 1/10, which is less than 1, so this converges. So we're comparing it to a convergent sequence, which seems like a good idea. So yeah, let's do a limit comparison test where we say the limit is k goes to infinity of 1 over k times 10 to the k divided by 1 over 10 to the k. So we're saying, does this thing behave like a 1 over 10 to the k? All right, let's flip and multiply. So we get limit is k goes to infinity of 1 over k times 10 to the k times 10 to the k over 1. So the 10 to the k's cancel. And I'm just left with the limit as k goes to infinity of 1 over k. And what is that? That's 0. Now, this is kind of one of those special cases, right? If the limit comparison test gives you 0 or infinity, you have to be a little bit careful. But the rule is, if you get 0 and the bottom thing converges, then the top thing converges. And we know that the sum of the bottom does converge, so the limit comparison test tells us that the sum of the top also must converge, yes.
And why is that the exception, I guess? The convergence?
The reason why is that it doesn't, okay. If this thing goes to 0, this is kind of what I was saying before. If this thing goes to 0, it means that the top is getting smaller faster than the bottom is. And what I'm saying is, okay, I know that the bottom converges, but this is much, much smaller. Now, it doesn't work the other way, because let's say that this diverge. And I'm saying, so this diverges, and this is much, much smaller than this. Being smaller than something that diverges means you could either diverge or you could converge. So it's inconclusive.
Okay.
Does that make sense?
Yeah.
But if it's 0 and this one converges, then this one is forced to converge as well. Yeah. Okay, so what we get then is, therefore, the sum k going from 1 to infinity of 1 over k times 10 to the k converges by the limit comparison test. And we're done. I hope everybody is able to see from some of these problems that doing the problem takes almost no space on the page. All of it is knowing what to do. Okay, and this just kind of goes back to what I was saying last time, that it's not about, the game is easy if you know the rules of the game. So learn your rules really, really well, and then you do well on this exam. Other questions? Let's see, somebody wrote something. 32. Sure. Okay, number 32. We have sum k going from 3 to infinity of the square root of ln of k over k. Now again, this is a great example actually of us just using our brains for a second and saying, what do we think is going to happen? Do we think convergence will come out of this thing? Or do we think divergence will come out of this thing? And so what if the top were 1? What would happen? It would diverge because it's a harmonic series, correct? So if the top were 1, we just get harmonic. which diverges. The top is bigger than that. So this is something that's bigger than the harmonic series. So what do you think is going to happen? It's going to diverge. Okay, I agree. That looks like a divergent series to me. The question is, how do you test for it? So first of all, you could just do a comparison test, right? That's probably the easiest way you could go here, is you could just say, well, come on, this is bigger than the sum k going from 3 to infinity of 1 over k, right? Which diverges. And so this thing is bigger than a divergent series. So it diverges as well. And so you can say, therefore, the sum k going from 3 to infinity of square root ln k over k diverges by the comparison test. Yeah, so this is the kind of thinking that I'd like you to get into in this section. And actually, in some ways, these sections all combined with all of these tests, it feels a lot more like real mathematics than calculus usually does. Like calculus, usually we're computing things, right? It's like, here's an integral, find this definite integral. That's not really what upper division math feels like at all. Upper division math feels like this sort of thinking. It's like, show me why something is true. And then you have to create some sort of an argument and show that it's true. Yeah.
So in that last one,
yes.
3 is like the first point where the square root of natural log of k is like just bigger than 1.
Yes.
So if that was like starting at k equals 1, would you not say that anymore?
Yeah, it's not so good because if it was, yeah, so they're choosing something so that this isn't like a big fat mess, right? They don't want it to be 0. And I think that they just want to make sure that this is an easy comparison test to make. Now, what would you do if they did start at 1 is your question. Well, what I would say is like, okay, forget the first few terms, right? And this is what you would kind of do, although they're nice enough not to make you do it, is they would say, okay, the first few terms, this isn't true. But then afterwards, after k gets to 3, this is true. And so I don't really care. So this diverges. And if I add a couple extra terms onto it, it still does. So basically, if the 3 to infinities add up to infinity, then if you add a couple more things on, it still adds up to infinity. Does that make sense? So you could like cut it into some pieces and say, well, the first 2 terms aren't technically bigger than this, but then afterwards they are. And so that diverges. And then plus those 2 terms that I cut off, that still diverges. So I don't think the book will ever make you do that, but that is the kind of thinking that we would do like in real analysis, is it's kind of like, okay, take the first n term, set them aside, and then after the nth term, all of these terms are bigger than these terms. So these terms diverge. So this diverges, add on a finite number of numbers to infinity. You still get infinity, yada, 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 diverges. Yeah.
So if it converged, would you just add the first like nth number of terms?
Exactly, because if you add up a bunch of things and they converge, then if you just add finitely many more numbers to it, it converges. So if it adds up to 3 and I add on 6 and 7, I'm good to go, right? Yeah. Okay, we are out of time. So tonight, the only thing that will be due is 10.5. Monday night, we'll do 10.6, 10.7. Okay, have a great weekend.
Thank you.
Yeah.